Welcome to the presentation of Understanding Choice Independence and Error Types in Human-AI Collaboration, which is joint work between me, Alexander Erlei, Abhinav Sharma, and Ujwal Gadiraju. As I guess everyone watching knows, nowadays both experts and laypeople constantly use and interact with algorithmic decision-making systems, be it in a working environment or just in everyday life. For instance, we can look towards the medical sector and observe that physicians routinely receive assistance by different software and large language models like GPT-4, which are able to not only provide diagnostic assistance, but also analyze imagery quite accurately. On the laypeople side, online users repeatedly report high levels of satisfaction from AI responses compared to the responses from actual human physicians, be it through online forums or even just by utilizing the web interface of LLMs like GPT. For the legal profession, there are many papers showing that algorithmic predictions can, in theory, strongly increase the efficiency of, for instance, bail decisions. And again, there's evidence that even lay clients are able to utilize software such that they are able to generate outcomes that are comparable to outcomes they may receive with human expert assistance. And finally, of course, there's a plethora of consumer recommendation algorithms that often span multiple categories, such as Spotify's algorithm, which basically offers suggestions for mixtapes, playlists, artists, podcasts, for a lot of different things. And as these examples illustrate, algorithmic decision-making systems often perform not one, but multiple tasks. A weather app does not only predict temperatures, but also sunshine hours, wind and rain. And this holds for the majority of algorithmic systems, and even more so for generative foundational AI models like LLMs. However, the fact that algorithms perform multiple tasks also implies that users regularly observe different performance levels. If you ask ChatGPT, for instance, for Python code, it is pretty reasonable, but the performance for Stata commands is noticeably worse. And you can basically find an infinite number of examples where a system may provide very good predictions for some problems, but breaks down for others, which is a point that is often raised in medicine because there are so many exceptions, so many rare conditions for which there's comparatively little data to train models with. And this fact of heterogeneity in performance means that human decision makers or users need to be able to distinguish between good predictions and bad predictions and then make rational choices in order to exploit all the benefits novel algorithmic systems can offer society. Another way to say that is that human decision makers need to adhere to choice independence. And to illustrate the concept, imagine that there are two problems, triangle and circle. In addition, there's an algorithm that provides good predictions for both problems, which exceed the accuracy of a human alternative. A rational decision maker would now choose to delegate the prediction to the algorithm and forgo the human alternative because the algorithm supersedes the human in accuracy. Now, imagine the case where the model makes good predictions for a triangle, but bad predictions for circle. In that case, the correct choice would be to delegate triangle predictions to the model, but use the human forecasters for circle. Now, we can imagine, however, another scenario in which, again, a decision maker delegates both problems to the model, providing two good predictions. However, once the model makes bad predictions for circle, the decision maker not only opts for the human for the circle problem, but also forgoes the model in the triangle problem. Right? For instance, because they wrongly generalize the model's errors in the circle domain to the model's quality in the triangle domain. Now, this would be irrational. It would hurt over accuracy, and it would be a violation of choice independence because objectively the model's performance in circle is independent from the model's performance in triangle, which should be incorporated into the human decision maker's choice rule. The two performances should be judged independently from one another. And in this project, we want to test this. We want to test whether the independence axiom of choice holds for delegation decisions in human AI collaboration. In addition, we're interested in the effect of expertise within that choice independence framework. What happens, for example, if the model is good for triangle, pretty bad for circle, but also if the human has expertise in the triangle problem, but no or little expertise for the circle problem? How does the human delegate, and how does the human's own expertise relationship with the problem mediate their delegation decision? And we could ask the same question for situations in which the model makes bad predictions for the problems the human has expertise in, but makes good predictions for problems the human has no expertise in, which would relate more to lay people, whereas the first model would be more akin to an expert system, assisting, for example, a physician in medical diagnoses, compared to the second one, which is a complementary system, which are often used when aiming to maximize overall accuracy or efficiency to minimize expertise overlap or redundancy. And following that framework, we also ask, does the human's level of expertise affect their adherence to choice independence and consequently their reliance on AI through delegation? Finally, we are concerned with the type of error algorithms can make, originating from both either the environment or the model itself. It is a well-established concept that humans struggle to properly evaluate algorithms in the presence of forecasting errors, and here we differentiate between moderate but high-frequency continuous errors and rare but large errors to determine whether human reliance on AI system is dependent on the environment's randomness function or the AI system's systematic forecasting bias. Now to the experimental design. We use an online prediction experiment in which participants take on the role of a farmer who has to predict the irrigation need of two fictional crops, memaseed and wusanat. Memaseed is our human expertise domain, and wusanat is our complementary AI expertise domain, meaning we design it in such a way that humans will find it difficult to solve. Irrigation need in our task depends on three input factors: sunshine, average day temperature, and wind speed. And the relationship between the three input factors and the output factor irrigation need is unknown to subjects. However, they can learn it through descriptive information and learning rounds. In addition, for memaseed, the human expertise domain, subjects also receive a decision rule which allows them to make good heuristic predictions. Participants then can choose to either predict irrigation themselves or rely on an AI system, and the more accurate their prediction, of course, the more money they earn. And here, an illustration of the procedure. Subjects begin with the instructions and then answer 4 comprehension questions. Those who fail 2 times are not allowed to participate. Then they are randomly assigned to one of 6 treatments, differentiating the AI system's type and the environmental error. And then participants proceed to a descriptive learning phase, an experiential learning phase, and finally complete 10 official rounds, each of which consists of 2 simultaneous predictions, one for the human expertise domain and one for the complementary expertise domain. Here they also decide whether to rely on their own prediction or the prediction of the AI system, and note that participants did learn about the performance of the AI system during the 2 learning phases, so they make an informed decision on whether or not to delegate. Here a quick overview of the relationship between input and output for both fictional crops, as well as the intervals from which we draw the input numbers. And here an example of the descriptive learning phase. First, participants see a table documenting input and output numbers, as well as the AI system's prediction. And second, they also observe the AI system's error curve for the 2 crops, which they will make predictions for. And in the experiential learning phase, subjects make 10 predictions, then using 3 input numbers for both crops to then again receive feedback. And here you can also see the decision rule subjects receive for memaseed right below the title. And this is how feedback in the training round looks like, which they receive 10 times. And then finally, this is how the delegation decision during the official rounds looks. Now to the treatments. We deploy a 2 times 3 between subject design, differentiating between continuous and rare environmental randomness, as well as 3 different AI systems: best possible AI system, complementary, and substitute AI system. The environmental error is either drawn from a uniform distribution -5 to 5 in the cont treatments, or from -27 with a probability of 20% in the rare treatments, which also have a 80% probability to draw a random error of 0. The 3 AI systems can be differentiated as follows. The best possible system always makes the best possible prediction, and the only error is the environmental random error because one cannot predict randomness. The substitute system is a substitute for the human, meaning it makes the best possible prediction in the human expertise domain, but exhibits systematic errors in the complementary domain. And similarly, the complementary systems makes the best possible prediction in the complementary domain, but exhibits systematic errors in the human expertise domain. The systematic error always depends on the environmental error. If the environmental error is continuous, the systematic error is rare. And if the environmental error is rare, the systematic error is continuously drawn. The expected value and average errors are of course always the same between treatments. And here's some descriptive information about the participants. But now onto the results. First, we are looking at performance and check whether our manipulation and treatments work as intended. Here we see the average prediction error of both the subjects and the model during the training and the official rounds for all 6 treatments. The bold cells are the cells where the system exhibits greater prediction errors than the average human participant. And what we can see is that the only cases in which humans outperform the model are the ones we aim for. Humans outperform the substitute model in the complementary domain and the complementary model in the human expertise domain. Thus, the prediction accuracy here is as intended. And to check subject perceptions, we ask them to indicate confidence in their own and the model's predictions after the experiment. On the left, we see confidences in themselves, in blue, and the AI, green, for memaseed, and on the right, for vusanat. And here we see again that our manipulation was successful. Humans have higher confidence in the model everywhere except for the complementary model for the human expertise domain and the substitute model in the complementary expertise domain. And thus subjects perceive the desired difference in AI performance. Now to our main results about choice independence. First, we look at the human expertise domain. If choice independence holds, there should be no differences in delegation between the best possible and the substitute model because both deliver the best possible memaseed prediction. Any difference in delegation would be solely due to the model's systematic error for vusanat, which has no objective bearing on the model's performance for memaseed. And here we see the share of predictions delegated to the best possible AI in green and the substitute model in blue. And we see that subjects are significantly less likely to delegate to the substitute model for both continuous and rare environmental randomness, which also translates into subject perceptions of the model, with subjects indicating lower confidence in the substitute model's memaseed predictions, as well as on a number of trust indicators. They indicate lower trust and predictability and stuff like that. Hence, we can infer that humans violate choice independence in human-AI collaboration when delegating to a substitute expert or an expert model, and systematic errors in the complementary expertise domain reduce delegation to the best possible model in the human expertise domain. Now we'll proceed to vusanat, the complementary expertise domain. Here, choice independence holds if there are no differences in delegation between the best possible and the complementary AI system, because both systems make the best possible prediction for vusanat. The figure on the left shows delegation shares with the continuous environmental error. The right figure shows delegation shares with the rare environmental error. Green is again the best possible model. Blue is the complementary model. And first, differences for the continuous error environment are qualitatively similar to the memaseed results but not significant. And second, we find that under rare environmental randomness, subjects choose the complementary model with a systematic bias significantly more often than the best possible model in the complementary expertise domain, meaning vusanat. And this again translates into different confidence values, which means again, we find that humans violate choice independence in human-AI collaboration by delegating to a complementary model. However, this time, systematic AI errors in the human expertise domain increase delegation to the best possible model in the AI expertise domain. So the effect reverses based on the human's expertise. And finally, we look at delegation shares to the best possible model depending on the environmental error. And in theory, there should be no differences between the two best possible AI systems because they both make the best possible predictions at all times. However, as we can see here, there are some differences, in particular indicating that subjects are less likely to delegate to the superior best possible AI system when the environmental error is infrequent but large. And this suggests that error type may indeed play a role in determining whether a user delegates their prediction to a superior model. To conclude, Human forecasters systematically violate choice independence in human-AI collaboration, and this effect depends on the expertise domain, where experts reduce reliance on an AI system after observing mistakes in an unrelated second problem, but people without prediction expertise increase delegation to a superior complementary model as compared to a model that always delivers the best prediction. Thank you.